Thank you, Laura.
Okay. Thanks a lot for having us. We're really excited to be here. Thank you for giving us the opportunity to present. Today with Alex, we're going to present our work on fractional water detection with VIRS and deep learning to enhance global flood monitoring. Next slide. Yeah, I probably don't need to give you the motivation too much given the context of this seminar. But so, as you know, flood have become a major issue, increasing in severity and intensity over the past couple of years. And so a couple of years back, we decided to start working on a global daily monitoring tool for fractional water detection that could be used for global flood monitoring. And this is actually the image you can see, one of the products of that tool. So this is a daily image of fractional water content of the world derived from VIRS with machine learning. Next slide. So this is our motivation for this work. Why do you want to do this? We wanted something that could be a global water detection tool for flood monitoring. And the main reason for that was to continue past effort. As you know, MODIS is being discontinued. I think actually stopped collecting data or is stopping collecting data this year. And a lot of the tools we had for global water mapping and global flood monitoring were based on MODIS. And so we wanted to create a tool to continue this legacy. Then the other motivation was that we wanted to make this tool or enhance this tool with current capabilities of deep learning, because deep learning has really improved our capabilities and advanced our field. And so we wanted these tools to be based on deep learning. And the final goal was to build a modern fusion-based fractional water detection algorithm. Next slide. So these are the highlights of what we achieved. We produce daily global fraction water maps. They are based on VIRS and Sentinel-2 dynamic world observation, so a fusion product. They predict the fraction of pixel covered with water per VIRS 375 meter pixels. So how much of that pixel is covered by water. They outperform existing NASA and NOAA VIRS flood algorithm, and Alex is going to extensively talk about the validation of our product. And it improves flood map accuracy and massively reduces false positive. So this tool for us really has, or this product for us really has the potential to enhance global daily flood monitoring for the general public. Next slide. Before I dive into the method, just a little bit about our team. So this started 3 years ago, and it's been a collaboration between the University of Arizona, where I was a postdoc then, and has since been spearheaded by Alex, who's still a PhD there, and has been a collaboration with NASA because they were interested in using or advancing the VIRS global mapping with deep learning. So a big thank you to the people at NASA for their support. Next slide. Yeah, let's go into the method. So why use deep learning at all for flood detection? Why not just rely on actually, can you go to the next slide, Alex? Sorry. Why rely at all on our deep learning? Why not just rely on a threshold-based algorithm or more conservative estimates like we've done before? So this removes the reliance on single pixel threshold. So as you know, this can work relatively well, but in some examples, this can be complicated, and deep learning learns through data and so can generalize to other situations that haven't been covered by simple threshold and manually selected threshold. And this massively reduces the number of false positive, mainly because deep learning uses spatial context and it explicitly considers the shape and the texture of flooded area. So this removes the importance of relying on ancillary and rule-based systems where we have to make a decision. And so it reduces also the need for manual intervention and corrections of maps down the line. And also because in the past, let's say 10 to 15 years, deep learning has shown to outperform those more classical approach. And there's a very large amount of successful research in that area. Next slide. So our first task to achieve this was to build obviously a data set. Deep learning, as you may know, requires a large amount of data, and so we had to build a data set with inputs and targets. So what are we actually trying to model? What are we trying to learn? So as you may have guessed, our inputs are VIR bands. We use both 750 native resolution VIR bands and 375 meter VIR bands, the ones that we deemed the most important for water mapping. And then our target is dynamic world, but rescaled at the visual resolution. So we take the 10-meter water, no water layer from dynamic world. This is about 9,600 by 9,600 pixels at the native resolution. And then per VIRS pixel, so 375 meter, we calculate the amount of the pixel that is covered by water for every VIRS pixel. So we rescale that one to 256 pixel per chips. And you see on the right, this is our pipeline. We take a VIRS grid cell at 256 pixels, so around 96 kilometers. We select the VIRS chips, and then we also sample dynamic world. We discard, because we have a large amount of data, we discard images that are only partially covered by dynamic world, that don't have any water pixel, or that have missing values. And then we resample it to 256, and we get this fraction of water extent, which is a value between 0 and 1 for every pixel. Next slide. So this was our sampling strategy to create an extensive data set. So we wanted to sample over all the biomes in the world, but we also wanted to make sure that we detected enough water, because if you sample just randomly, the probability of finding water pixel might be relatively low. So we mostly sampled around non-water bodies, rivers and lakes, etc. Next slide. And so this is the data set that we built. So here you have an image representing per grid cell, per VIRS 256 pixel grid cell, the number of chips in that cell, and also an example for some of those cell of the time series that produces of different chips for the grid cell. Overall, we have about 100,000 chips that we split into training, validation, and test. At the bottom, you can see that it's a good mix of water content per chips that is representative of the whole data set for the different splits. Next slide. For the modeling part, we decided to go with a tested and trusted model, the UNet, which has been proven to work extremely well in all sorts of tasks. We added a learned multi-resolution embedding. So we ingest the different bands at their native resolution and have a learned embedding that goes from 300 to 75 and 750 meters respectively to the first layer of the UNet. Then have a UNet, and then final regression head where we predict the fraction of water content. Slide. And yeah, this is one of the results. This is a flood over Pakistan in 2025 that you probably all heard about. And this is based on this algorithm for VIRS daily imagery, and we can really see the progression of the flood over those couple of months. Next slide. Yeah, but as we all know, all those algorithms need to be trusted. And so there's nothing more important than validating an approach. And so here I give it to Alex, who's going to talk how extensively our validation process has been.
Thanks so much, Jonathan, and hi everyone. Great that so many of you were able to join today's webinar. Yeah, I have the fun task of talking us through some of our really interesting validation examples. And so our overarching aim with our validation was to be able to really holistically sort of understand and quantify and report the flood mapping accuracy of this algorithm, but also to be able to sort of explain the model behaviors and especially under known sort of failure modes and edge cases, um, to really show to NASA and hopefully its eventual users of this algorithm that this algorithm is robust to detecting surface water anywhere around the globe. And so it was split into a four-stage process. The first three of those stages were a quantitative validation, so comparing the water extent predictions from our model against several different reference data sets. And for those, we primarily used Sentinel-2 and Sentinel-1 based flood detections. And then in the fourth stage, we did a qualitative evaluation of manually selected problem scenarios. And you can see the distribution of these on this global map. And in total, these areas cover nearly 10 million square kilometers, which is equivalent to around 8% of Earth's land area once you exclude Antarctica. So the first of those stages, global water instances, this was actually the test group from the training data set that Jonathan already showed us. So those chips that we held out from that, nearly 10,000 chips across nearly 1,000 locations, and we used the Sentinel-2 dynamic world as our reference data there. That was a mix of permanent and non-permanent water. And so given that this is a sort of flood monitoring project, we then sampled events from the global flood database and ended up with nearly 1,000 chips from around 100 flood events. For those, since a lot of them do have kind of naturally very cloudy conditions associated with real life flood events, we use Sentinel-1, taking advantage of the synthetic aperture radar from Sentinel-1, being able to map the floods despite the clouds. And then we sort of saw how well our VIIRS algorithm was able to keep up with that. And then we looked in a bit more detail at selected flood events. So we selected nine other events from the Dartmouth Flood Observatory archive that had coincident Sentinel-1 and Sentinel-2 coverage. So we could look really in detail and visually inspect how our model was doing, and also referenced sensitivity test our two reference data sets. And finally, we manually selected 19 problem scenarios, which are known to be challenging for optical satellite water detection methods. And we kind of use harmonized Landsat Sentinel-2 just to guide our visual expert ratings that we assign there. So this is some outcomes from that first validation stage, just showing some example chips from several of the continents. Just to situate your eyes, the third column is the dynamic world reference data, and the fourth column there is our algorithm prediction. And so overall, our model does do a good job of capturing the overall water patterns that we see and the diversity of the types of water bodies that we captured in our training data set. And so across those nearly 10,000 chips, those are our aggregate statistics. And one nice thing to point out is that overall we had a mean error of less than 1% water extent compared with our dynamic world reference. So pretty marginal bias overall, which was good to see. And then if we look at those by continent and biome, those are the results there. Pretty limited variability by continent, which is great to see. And also by biome, we do see a little bit more variability. Those are the 14 global biomes there that Jonathan showed on that map earlier on. And most of those achieving an R-squared score of 0.7 or 0.8. So explaining a really good high proportion of the variance in our reference water extent data. So moving on to our second validation stage, and this is looking at around 100 flood events from the Global Flood Database. This is just one example from Australia in 2017 associated with Tropical Cyclone Debbie. And again, to situate your eyes, the first row are the VIIRS scenes. So we have a true color image and then a false color composite made up of the shortwave infrared and near infrared and red bands. And then in the second row, the first one there is our model, and then comparing that with existing VIIRS algorithms. So we have NASA's global flood product, and that's their VIIRS algorithm, which was launched sometime last year. And we also have the NOAA and George Mason University, NOAA GMU, VIIRS flood product shown there as well. And then in this example, our reference data, we were using a deep learning algorithm for Sentinel-1. And so you can see that our model is doing a good job of capturing that sort of large flooded area in the center of the scene, but it's also doing a really good job of picking up some of the finer scale details. And so when we look at that across all of those 100 flood events, these are our aggregate statistics. If we look across at the R-squared value, certainly lower than we saw in our first validation stage, and that kind of reflecting the difficulty with capturing flood waters compared to capturing a mix of permanent and non-permanent water. But our model surpassing some of the existing VIIRS algorithms. And then once we look at that aggregated by flood severity, just interesting to note that our model has pretty consistent sort of error by those groups, whereas some of the other VIIRS algorithms seem to sort of increase as you move towards more extreme flood events. Okay, and then our third validation stage, we looked in a little bit more detail, and we also have the benefit here of having both Sentinel-2 and Sentinel-1 reference data, so sort of two complementary reference data sets to look at. This is an example from a flood event in Greece. Some interesting differences here between the VIIRS algorithms that you can probably start to see with your eyes there. But something I wanted to point out is not only the detection of flooded areas, but also just making sure that we don't pick up false positives. So you can see in the NASA example, quite a few of those sort of cloudy or snow and ice areas in the mountainous areas being picked up falsely as water. And luckily, our model was able to learn that those were not indeed water. And I just wanted to show one more flood event from that validation stage, and this one's from Somalia. I like this one because this was a pretty the flooded area here was actually along a very small river channel, and so this is really naturally a challenge for VIIRS methods that use moderate resolution data. And so this event, as you can see, was mostly missed by the other VIIRS algorithms, although you can see it mapped quite nicely from Sentinel-2 and Sentinel-1. And our model, it isn't perfect, but it does at least pick up some of that flooded extent that is missed by those other algorithms. So that's positive encouragement for global flood detection. And just summarizing on those results for those three quantitative validation stages. So our algorithm, ML fractional water detection, outperforms existing VIIRS flood algorithms for all of those three validation analyses that we conducted. And if we look at that second stage where we looked at 100 flood events, we have pretty significant improvements on the existing VIIRS flood algorithms that are used operationally. And our fourth stage was a really fun one. And thanks to Dan for Dan Slayback for his help on this. Trying to select these problem scenarios around the world where we knew that the current algorithms are often challenged. So one of these was some flooding that occurred in the desert in Libya. And it was great to see that our model was able to pick up this water in this very sort of unusual environment. And this one was an interesting example too. This is actually some volcanic material in the USA. and was known to be a challenge for NASA's current VIIRS algorithm that often mistakes this type of land cover for water since it looks very similar. It has this sort of dark appearance. And we were pleased to see that our deep learning algorithm was able to learn that this wasn't water, so consistently avoids false positives from volcanic material. And so Dan kindly assisted with this sort of expert rating process, and you can see our results there for each of those categories. This is across the 19 problem scenarios that we came up with. And just comparing against the current NASA product, our model was able to get higher qualitative scores in all of those categories. So what's the outlook then for this algorithm? Just summarizing some of the strengths from our validation. We believe that it reliably detects surface water in varied global contexts, and it significantly improves on existing VIIRS flood mapping techniques. One aspect of that is that it reduces the likelihood of false water detections, which is obviously really helpful. And we like the fact that it has this fractional water estimate, which I think gives you a more sort of information-rich output than a binary output can. One thing we also had to test was how well it generalizes to different types of VIIRS imagery. So all of the training we did was using the Suomi MPP satellite. And we just readily applied our algorithm to data from the NOAA 20 satellite and found that the predictions look just as good. This is an example here from the Republic of Congo, and the first row is using Suomi MPP data, and the second row, second row is using NOAA 20. And really the main differences in the water extent outputs are driven by just shifts in clouds between the overpass time of these two satellites. Some of the weaknesses, we did see some false positives due to terrain shadows, and we actually think that those seem to be inherited from our dynamic world training data. So that's just a limitation of this sort of weak label approach, something that hopefully we could fix in future. Probably thinking operationally, it's simplest to try and fix that with some post-processing, but there could be a longer study actually to try and remove those a bit more holistically during the training process. Really fine scale water features are still hard to detect just by nature of this being a moderate resolution product compared to those medium resolution sort of Sentinel satellites. And that's an example there where just some small river channels not being picked up by our model. And cloud cover, as with any optical method, is an issue. And so this example shows you some false negatives from cloud cover where the Sentinel-1 algorithm is sort of obviously really nicely picking up that water content since it's able to penetrate through cloud with the synthetic aperture radar. And just to point out as well, this algorithm is really optimized for flood monitoring, and so hasn't really been tested in the realm of sort of mapping large-scale changes in Earth's surface water. On the second to last point on the last slide, I said that clouds are an issue, and they certainly are. However, one really cool aspect of the algorithm that we saw and was sort of surprising to us was we are actually able to detect some degree of water through thin clouds. And so you see the Sentinel-1 reference on the left, and then here's our model. It is missing quite a lot of the water, but compared to some of the other VIIRS algorithms, it is able to detect water through those thinner cloud areas. And so we looked at this comprehensively across the 100 global flood database events and just plotted this as a function. So function of error as a function of increasing cloud thickness. And what this sort of shows is that our model, the error increases much more gradually as cloud thickness increases. So we think this is a strong sign that we are able to detect water in these thin cloud conditions where current approaches typically are prohibited from detecting water. So just some of the prospects for deep learning in routinely generated flood products. We think that this project shows that deep learning can consistently improve flood extent estimates and reduce false positives. And so surface water detection and flood mapping could indeed benefit from using deep learning methods, either in place of or in complement to the classic methods that underpin current near real-time products. And so we're actively sort of working with NASA at the moment to see whether there are resources to deploy this as part of its near real-time global flood product. And if so, I think that would make this the first deep learning based, routinely generated global flood data set with daily coverage. And I think this shift is an interesting one and sort of echoes a little bit what has been seen in the hydrologic flood forecasting space, where things like long short-term memory networks and transformer networks have become pretty well established as leading approaches used in operational flood systems. So I hope I didn't run too much over time there. Thank you so much for listening. These are some resources here if you are interested. We have an inference code to actually run this algorithm. We have our pre-trained weights. You can access that on the Social Pixel Lab GitHub page. The link is up there. We've also published our validation data. So those 4 validation stages I've shown you, you can actually obtain the reference data for those if you wanted to use that for future algorithm development. We would love to see that used. We have a preprint of our paper that is out now. And yeah, just a final big thanks to all of our collaborators who put a lot of effort into this project. And just to mention that this work was partially funded by several NASA awards, for which we're very grateful. Thanks so much for listening, Jonathan. Feel free to pitch in. Otherwise, I don't know if we have time for questions. Lara, Albert.
I would
Thanks a lot.
squish a few questions. Albert, what do you think? I think it was amazing. Jonathan and Alex, really nice one. Well done.
Thank
Thank
you.
you.
Same
Okay.
here. Yeah, I think we have, time for a few minutes for questions. And I saw some questions in the chat, actually.
Yeah, I had some, but I will post them in the chat so you can answer during the next presentation so I don't take time. But it's incredible, really. I was going to ask how to access it, but you already gave this here, so it's pretty fantastic. Okay.
Yeah,
So
for the model is open and anyone can use it.
Mhm.
Then I don't know, Alex, have you looked at burn scars?
I'm sorry, I haven't looked in the chat yet, if that's what you're referring to.
So the question is, have you looked or analyzed how this product is performing related to misclassification of burn scars as water false positives? Other Veer-based flood maps are known to have misclassification of burn scars as water. I don't remember if we looked at.
No, actually, that's one class or category that we missed off our validation. So that is something that we could add. Our problem scenarios, we looked at volcanic material, cloud shadows, terrain shadows, some snow melt related flooding, some desert floods, flooded vegetation. But yeah, we'll add burn scars to that list. It will be interesting to see if this deep learning approach has managed to learn that effectively.
And then there's a question, do you intend for end users to access the right data that you process for rapid flood mapping events or prefer that end users run the model themselves? So we are currently, we've been working with NASA for the past 3 years. And so there's a process to maybe deploy it on their server as a product, but that is still in progress. Needs a lot more validation. In the meantime, as Alex mentioned, it's openly available and people can run it.
Yeah, and this is a bit of a preview, but there is another member of our research group who's sort of been using this for another project, and they've actually done a nice extension where they've been able to apply this to Veer's data from Google Earth Engine, which does sort of speed up the overall process. So it may be, yeah, don't want to make promises, but there may be a slightly updated pipeline in the near future, which would also be made publicly accessible, and I think would make it even easier for users.